Hi class, welcome to exercise 3H, irrational indices. In this lesson, your examples and pre-learning will be example 19, writing in the index form. And your pre-learning for this example will be questions 1, 2 and 3 in the new book and 4 and 5 in the old book. And then we'll do example 20, where we'll be writing in surd form. And for this example, your pre-learning will be questions 4 in the new book and question 6 in the old book. And then finally, we'll do example 21, where we'll be evaluating numbers with fractional indices. And in this example, your pre-learning will be questions 5 in the new book and question 7 in the old book. So welcome to this unit. It won't be a long one, but it does depend on having mastered the first unit on indices and surds, especially index laws, including those that involve negative indices, as well as multiplying and dividing surds. Of course, I will refresh those as we go, but if you need more than a quick refresher, make sure that you read over those OneNotes, re-watch the videos, and revise some of the exercises. Alright, so if that's you, you better head off and do that now. Otherwise, I'll see you in the introduction. Okay, you need to recall the index laws and their negative friends. And I've cut these out of those lessons that we did earlier in the year. Hopefully you already know all these, because it's really important that you're comfortable with why they're true, because we'll be using all of those reasons throughout this unit. So if you have any doubts, please revise the first 2 lessons of the indices and surds unit. But a basic summary of these index laws is probably needed, okay? So what law 1 and 2 say is, if we have the same number as the base, they can interact even with different indices. So for example, 2 to the 3 times 2 to the 4 is equal to 2 to the 7. Or 2 to the 3 divided by 2 to the 4 is equal to 2 to the minus 1. And what law 4 and 5 were saying is if we have different numbers as the base, they can interact with each other if they have the same index. So for example, 2 to the 4 times 3 to the 4 is equal to 6 to the 4. Or 2 to the 3 over 5 to the 3 is equal to 2 over 5, all raised to the 3. And you might have noticed I skipped law 3. Well, law 3 is saying that a power raised to a power just multiplies those indices. Okay, hopefully you're comfortable switching between powers and indices as basically meaning the same thing. It just sounds silly if I said an indice to an indice, okay? So for example, if we consider 8 as 2 to the power of 3, I can rewrite 8 to the power of 4 as 2 to the power of 3 raised to the power of 4. Okay, so that's nothing more than subbing in the 2 to the 3 for the 8. But because I got 2 to the 3 raised to the power of 4, well, that ends up being 2 to the power of 12, because I've just multiplied the 3 and the 4 together. And finally, the other concept we need to recall from the first unit are those surrounding surds and roots. And as you know, the definition of the expression the nth root of x equals a is what is the number a that is equal to x when it's raised to the nth power. Or in other words, the nth root of x equals a is true when a to the n equals x. So a common example us teachers like to use is the cube root of 8 equals 2, because 2 cubed is 8. I suppose that's because we've got a power that's greater than 2, and 2 is a nice easy number. And it's also worth mentioning that the square root is the second root. It's just a matter of convention that we don't write the 2. Okay, so in this lesson, we're going to put all of these ideas together to start to learn all about rational indices. So hang on for a second there. We've worked out that a to the m is multiplying m a's together. And it's pretty easy to understand multiplying that countable amount of a's together. Whereas a rational number is one that we could represent as a fraction, and that includes numbers like 2/3, or a whole number like 4, or even 64 on 1017. So what the heck does a rational index mean? So to figure this out, we're going to actually have to put together what we know about roots and index law 3. So if a to the n is equal to x, then the nth root of x is equal to a. So that's just the definition, right? So because a to the n equals x, we can now sub it into that root in the place of x. So that would mean that the nth root of a to the n has to equal a. Okay, so that's what we know about roots. But if we imagine that we could think about that nth root as some power, then a to the n inside that power is going to equal a. And a just means a to the power of 1. And also, I hope you realize I'm just using r because it's a good letter to say root, okay? So now we've got a to the n raised to this magical power of r, and it's equal to 1. So that means that n times r must equal 1 just using the third index law. So it doesn't take much to see that if we divide both sides by n, r must equal 1 over n. And these two concepts together, the roots and the index law, give us our definition of the rational indices. And that is that the nth root of x is just equal to x raised to the power of 1 divided by n. And of course, mathematics being the consistent thing it is, all index laws apply to rational indices. And this means that the first three laws allow us to create any rational number as an index. So let's have a look at that using a whole number index with an nth root. So by law 1, a to the m times a to the 1 on n is equal to a to the m plus 1 on n. And expressed using a surd or a root, that is a to the m times the nth root of a. So a little number example I could use here is 7 to the 5 times the cube root of 7 will equal 7 to the 5 plus a third, which we can simplify to 7 to the power of 16 over 3. So you can see we've gone a long way here. It's not just 1 on n, so to speak. We could recreate any rational number we want. Let's have a look at that in law 2, where I've got a to the m divided by a to the 1 on n will equal a to the m minus 1 on n. And that's the same as saying a to the m divided by the nth root of a. And a number example for this one could be 5 squared over the cube root of 5, which is equal to 5 squared over 5 to the third, which is the same as saying 5 to the 2 minus a third, which is 5 to the power of 5 divided by 3. And I'm just going to write out the next few laws without explaining them too much. So law 3 would mean if we had a to the m raised to the power of 1 divided by n, well, that equals a to the m on n, which is also the same as saying the nth root of a raised to the power of n, or the nth root of a to the m. Okay, so that's another way you could create some rational numbers. Now in law 4 and 5, it isn't necessarily about creating different rational indexes, but let's have a look at them at play. Okay, so law 4 would say if I had two numbers, a and b, and I multiplied them together and raised the whole thing to the power of 1 on n, that's the same as saying a times 1 on n times b times 1 on n. And that's just equal to the nth root of a times the nth root of b, which is equal to the nth root of a times b. And similarly, law 5 has a on b raised to the power of 1 on n is equal to a to the power of 1 on n divided by b to the power of 1 on n. And of course, we could convert that into root form. So that's now equal to the nth root of a divided by the nth root of b, which is the same as saying the nth root of a on b. Now, if you cast your mind back to the surds unit, we've already seen some of laws 4 and 5 when n equals 2. So for example, the square root of 8 was equal to the square root of 4 times 2, which is equal to the square root of 4 times the square root of 2. And because the square root of 4 is 2, we can rewrite that as 2 times root 2. Now let's try that with rational indices. So the square root of 8 is equal to 2 to the power of 3 square rooted. Okay, and that's just because 2 to the power of 3 is equal to 8. So as an index, the square root is equal to the power of a half. So we've now got 2 to the power of 3 raised to the power of a half. And index law 3 says that that's 2 to the power of 3 divided by 2. Okay, because that's what 3 times a half is. So the question is, are these different answers? Well, no, they're not. So let's start with the first answer, 2 times the square root of 2. Well, that's 2 to the power of 1 times 2 to the power of a half. And using index law 1, we now get 2 to the power of 1 plus a half. And 1 plus a half is equal to 3 on 2. So just a quick inspection using index law 1 showed us that these two different ways of expressing the problem actually is the same answer. Alright, I strongly suggest that you pause the video and do the building understanding questions in the new book, which translates to questions 1, 2 and 3 in the old book, because it's really important to experiment with the numbers that you know the powers of, just so you can see this working before we explore this concept in greater detail. Alright, so head off and do those, and then come back and see me in the next section. In this section, we'll be converting from root notation into index notation. So as we've demonstrated in the introduction, the nth root of a is equal to a to the power of 1 over n. And that also means that if you have the nth root of a to the m, well, that's equal to a to the m raised to the power of 1 on n, which is equal to a to the power of m divided by n, because by law 3, m times 1 on n equals m on n. And also, if you see a number a raised to the power of n multiplied by the nth root of that same number a, then we can convert that to a to the m times a to the 1 on n, which equals a to the m plus 1 on n by law 1. And of course, it's much nicer to neaten that up with m plus 1 on n equal to m times n on n plus 1 on n. And that's just multiplying m by n and dividing it by n to try and get the same base there. And so that is now m times n plus 1 on n. So what that means is you could rewrite a to the m plus 1 on n as a to the mn plus 1 all on n. So while this algebra might be great for your notes, it might not make a lot of sense until you see it work with numbers. So let's just say, for example, that m was equal to 3 and n was equal to 5. Then a to the m plus 1 on n is actually a to the 3 times a to the 1 on 5, which by law 1 we know is a to the 3 plus 1/5. And doing that algebra quickly for you, you should re-express that as a to the 16 on 5. And we can look into this a bit later, but you could rewrite that using surds and powers again, alright? So anyhow, let's just jump straight into example 19. We're going to express the following in index form. Alright, first off in part A, we've got the square root of 15. Well, that's just equal to 15 to the half, because as we know, the square root is the same as saying the second root. Alright, that's not much of a challenge. So let's just move on to part B, where we have the square root of 7 times x to the 5. So the first step is to turn that root into an index form. So we've now got 7 times x to the 5, all raised to the power of a half. And then using index law 4, that's equal to 7 to the half times x to the 5 raised to the half. And then index law 3 says we've still got our 7 to the half there, but we've now got x to the 5 on 2 as well. Of course, you could re-express 7 to the half as the square root of 7, but that sort of defeats the purpose of what we'll try and do, okay? So let's move on to part C, where the question is 3 times the 4th root of x to the 7. Now, the 3 is just hanging there, so we're not going to touch that at all, but we need to use the 4th root and turn that into the power of 1/4. So we've now got 3 times x to the 7 still, all raised to the power of 1/4. Alright, and as I said, we're not touching the 3 because it's not part of the indices. Alright, and so the only thing we've got left to do is multiply the 7 by a quarter. So we've got 3 times x to the 7 on 4. So hopefully you can see the difference there, how we use the 7 when it's inside the root compared to the 3 that was sitting outside of the root. Alright, finally part D has 10 times the square root of 10. Now I wonder if you can recognize what this might be from our surds unit. Anyhow, I'm going to move on to the next bit. We've got that 10 sitting there, and of course the square root is 10 to the power of a half, so that's 10 times 10 to the power of a half. And we can rewrite that as 10 to the power of 1 times 10 to the power of a half, because we've got the same base here. And using the index laws, that means we could now rewrite that as 10 to the power of 1 plus a half, which of course is 10 to the power of 3 on 2. Now for the exercise questions you're about to do, that's all you actually have to do. But just to compare what we did in the surds unit, we could rewrite that as 10 to the 3, all raised to the power of a half. Okay, so that's just using law 3 there. Now 10 to the 3 is 1,000, and a half is the square root, so I could now re-express that as the square root of 1,000. We're going to do more of this in the next section. Hopefully you can start to draw some good connections between the many ways that we've learnt to express numbers or algebra this year. Alrighty, right about now you should be pausing that video and doing questions 1, 2 and 3 in the new book, or questions 4 and 5 if you have the old book. And when you've done those, we'll see you back in the next section. In this section, we're going to go back in the other direction than we did in the last one. So we're going to be converting indices back to surd form. Well, it might not necessarily be back, but anyhow, let's do it. Okay, so now remember that the definition of a to the power of 1 on n is equal to the nth root of a. And also, a to the power of m on n can be rearranged as a to the power of m, all raised to the power of 1 on n, because that's completely consistent with law 3. And by consistent, I mean, you know, we've been moving back from the right direction to the left, and because it's an equal sign, you can move from left to right, right to left, okay? All right, and now we've got a to the m there, and we know that 1 on n is the nth root, so we could re-express it as a to the m inside the nth root, which when you see it written as numbers, you might think of it as the nth root of whatever a to the m is. Okay, and just as I said in the last section, a lot of this might not make a lot of sense just written as algebra, but hopefully it's great for your notes. However, to make some good sense of it, let's move straight into example 20, where, surprise, surprise, we're going to express the following in surd form. Alright, part A, we have 3 to the power of 1/5. Okay, that's equal to the 5th root of 3. And that's not really an interesting question, of course, because all we've done here was just use the definition. However, part B, we've got a bit more work to do, because the question is 5 to the power of 2 over 3. Okay, so we could use the third law here and separate them out as 5 to the power of 1/3 all squared. And by definition, 5 to the third is the cube root of 5. So we've now got the cube root of 5 all squared. And I'm just going to stop there because hopefully you can recognize that that is just too complicated. It'll look much better that when it comes time to use the third law, we put the fraction on the outside one and have 5 squared raised to the power of 1/3. Because now we've got the cube root of 25. Alright, so they're just the two parts we want you to try for this example. So, but please, let's take a note that it's normally much better to express a to the power of m on n as the nth root of a to the m, compared with the nth root of a, all to raised to the power of m. Because in a normal case, a to the m will be a number. Alright, how about you pause that video now and do questions 4 in the new book or question 6 in the old book. And that's not a lot to do, so we'll see you in a couple of minutes, I'm guessing, in the next section. Okay, I think it's time that we see what rational indices do to actual numbers. Never fear, all the numbers in this section are going to be easy. And just in case you didn't do the building understanding questions, I need to make sure that you remember if x is equal to 2, 3, 4, 5, 6, 7, 8, 9, and 10, then x squared is equal to 4, 9, 16, 25, 36, 49, 64, 81, and 100. And x cubed is equal to 8, 27, 64, 125, whatever. I know that 10 cubed is 1,000. And regards what's in x to the 4 and the rest of these cubes, perhaps you could figure out. Totally not being lazy there. I'm doing it because I care about you and I'm trying to challenge you as a teacher, okay? All right, now on top of that, you're also going to need to remember the rules that I'm not going to state for a fourth time. But don't forget that this also applies to negative indices, such as a to the minus m, which of course is equal to 1 divided by a to the m. So therefore, a to the minus 1 on n is equal to 1 divided by a to the 1 on n, which is also 1 divided by the nth root of a. Anyhow, I think you'll be fine with the rest of it. So let's jump into example 21, where you're going to evaluate the following, but not using a calculator, which is maybe the mathematical version of no hands. All right, part A, we have 16 raised to the power of a half, which is just equal to the square root of 16, which is 4. Meh, come on, give us a challenge, boys. So part B, we've got 16 to the power of a quarter, which is the fourth root of 16, which is 2, because 2 to the 4 is 16, right? Still not super challenging, but anyhow, let's go on to part C, where we've got 27 to the minus 1/3. All right, it's getting a bit more interesting. So we've got to take into account that negative indice. So we've got 1 on 27 to the third. And of course, the power of a third means the cube root. So we've got the cube root of 27 on 1. And that's equal to 1/3, because 3 cubed is 27. All right, it's not super challenging, but maybe for some of you, without using the calculator, it will take a bit of thinking. And of course, the questions will get a little bit harder in your exercise. Anyhow, let's have a go at that by pausing the video and doing questions 5 in the new book and question 7 in the old book. And when you come back, we're going to summarize this lesson. At first, the concept of rational indices may seem bizarre without any explanation. But once we consider the nth root and then use the first index law, you can now raise a number to any power that you want. In the following lessons, we're going to use this concept to solve equations that we couldn't previously, and also introduce a new type of graph. Alright, so from this lesson, a successful student will understand how a rational index relates to the nth root of a number, know how to convert between bases with rational indices and surd form, be able to evaluate some numbers with rational indices, and be able to apply index laws to expressions involving rational indices. Alright, so work hard to get all those skills. I know it might seem like a lot of algebra and sometimes meaningless numbers, but trust me when I say that this type of exponentials is really important to explaining some of the most important things that us humans interact with. Alright, I'll see you in the next class, whether that's in a video or in the classroom. Bye.